Since we have learned how to evaluate iterated integrals, we are now ready for some application of iterated integrals like finding the area by double integration and finding the volume of solid by double integration. So in our discussion, we will consider the first application, which is finding the area by double integration. But before that, no, let us consider a solid and how do we find the volume under a surface which is z with a function of x and y. And we shall consider a solid where it is bounded above by z, which is a function of x and y, and below uh, bounded by the region R, okay, on the xy plane. And of course, we will consider later solid but bounded by different planes. So if we will let f be a function rather of two variables that is continuous and non-negative on a region R in the xy plane. Okay, so meaning z is above the xy plane or on the xy plane or above the xy plane since it is non-negative. Okay, then the volume of the solid enclosed between the surface z, which is a function of x and y, and the region R is defined by this. No? Volume is equal to the limit as n increases without bound of the summation of f of x sub k, y sub k times delta a sub k, where k goes from 1 to n. Of course, we will evaluate the limit as n increases without bound. And this Riemann sum is equal to the Riemann integral, the double integral of f of xy times the differential of a. So here we are considering again c as a function of x and y. Okay, above is the surface z. Okay, and below is the region R in the xy plane. Now, if we want to get the volume of this solid, okay, bounded above by z and below by the region R in the xy plane. Now, instead of using the rectangular element that we used to do or we used to have in finding the volume of solid of revolution, since we now have a solid itself, now not anymore in the xy plane but in three-dimensional, okay, then we will consider now an element, no, which is in the form of a rectangular parallelepiped whose height is equal to z, since the distance of the upper base from the xy plane is z, and whose base area is equal to the differential of a. So the height of the element is z, okay, which is a function of x and y, and the element here is the differential of a. The base is the differential of a, and the differential of a may be dx dy, or the differential of a is dy dx, just like what we had in the discussion on iterated integrals. When we have dx dy, this is horizontally simple, so we do first the inner integration in x, then outer integration is in y, so we call this as horizontally simple. And dy dx means, okay, integrating in y first, no, then the outer integration is in x. So we go from lower to upper then right to left. Okay, in horizontally simple, we go first left to right and then lower to upper. Okay, so just imagine that there are infinitely many rectangular posts here or rectangular parallelepiped, and the summation of the volume of the elements, the infinitely many elements here, which is the summation of the height z times the base area, the differential of A, okay, and getting the summation where k goes from 1 to n and evaluating the limit as n increases without bound gives us the volume of the solid, and it is equal to the double integral of f of xy times the differential of a over the region R. So again, the differential of a may be in the order dx dy or dy dx depending on whether it is horizontally simple or vertically simple, respectively. Hence, the volume, which is the integral of f of xy dA over the region R, is the double integral of f of xy dy dx if it is vertically simple, and y will go from G1 to G2 again. G1 and G2 must be independent of y, or it must be function of x, and the outer limits of integration a and b must be constant. So x goes from a to b, or okay, the volume is equal to the double integral of f of xy dx dy, horizontally simple, where x goes from h1 to h2. H1 and H2 must be independent of x, therefore it must be function of y. And y will go from C to D, where C and D are independent of x and y. Okay, so this is how we will get the volume of solid bounded above by the function z equals f of xy and below by the region R in the xy plane. Okay, now if we are interested with the area, okay, to find the area by double integration, of course, in module 2, we learned how to find the area of the region R by ordinary integrals, and we use the rectangular element. The rectangular element can be either horizontal or vertical element depending on the convenience. No? Okay, now if we are to find the area by double integration, no, we will find the area of a closed and bounded plane region R, and this is defined as the double integral of the differential of A over the region R. And to compute the area of the region R, we are actually evaluating the integral where f of xy is equal to 1 on the region R. Okay, we are actually considering a solid, okay, where the height is equal to 1. So in effect, the double integral of the volume of the solid is the same as the area of the region R since the height is equal to 1. Okay, now please take note that when we are computing for the area by double integration, if we are considering the region R, okay, let us say that this is the region R, okay, we are considering the element, okay, this is the element which is the base of the rectangular parallelepiped, okay, which is considered as the element in finding the volume of the solid. So this is dx and this is dy. Okay, and the differential of A is either dx dy or the differential of A is dy dx, depending on whether it is horizontally simple or vertically simple. Now, and this is equivalent to using a horizontal element, and equivalently this is using the vertical element. Okay, and to illustrate, okay, let us consider the first example, but this time instead of using this PowerPoint, we are going to use the uh, whiteboard. So we are going to compute by double integration the area of the region R in the xy plane that is bounded by x is equal to y squared and x plus y is equal to 2. Okay, so we do not know the limits of integration for the double integrals, okay? Hence, we need to know the region R, the boundaries of the region R. And we can do that by getting the intersection of the two curves, x is equal to y squared, which is a parabola opening to the right, and x plus y is equal to 2, which is a line leaning to the left. Okay, so we have x is equal to y squared, and x plus y is equal to 2. Okay, so if we are going to solve these two equations simultaneously, consider these as equations 1 and 2, and using equation number two is x plus y is equal to 2. Elimination by substitution, we can replace x by y squared. Hence, we have y squared plus y is equal to 2. And transposing 2 to the left member of the equation gives us y squared plus y minus 2 equals 0. Of course, the left member is factorable, and factors are y plus 2, y minus 1 equated to 0. And solving for the values of y, okay, by equating each linear factor to 0 gives us y plus 2 is equal to 0, so that y is equal to negative 2. And y minus 1 is equal to 0, giving us y is equal to 1. And if we will solve the corresponding values of x, okay, we can use the first equation, no? X is equal to y squared. So we will simply find the corresponding values of x for each value of y. So when y is negative 2, the corresponding value of x is 4. Okay, so when y is negative 2, x is negative 2 squared, or x is equal to 4. Hence, we have a point of intersection at 4, 2. And when y is equal to 1, x is 1 squared, or equal to 1. Therefore, we have another point of intersection at 1, 1. X is 1, y is 1. Hence, 4, 2, and 1, 1 are the points of intersection of the two curves. And if we are going to draw the region R, okay, let us sketch the region R in the XY plane. Okay, let this be the x-axis and y-axis. We have the points of intersection at 4, 2. X is equal to 4 and y is equal to 2. Okay, this is the point of intersection. Let us label it at 4, 2. And another point of intersection at 1, 1. Okay. This is, sorry. This should be negative 2. Okay, sorry. I forgot the negative sign. The point of intersection is at 4, negative 2. So at 4, negative 2, we have, wait. Okay, this is negative 2. So this is the other point of intersection at 4, negative 2. And the other one is at 1, 1. So we can now draw the line x plus y is equal to 2. Okay, take note that a line at 2 points determine a straight line. So just connect the 2 points of intersection, and this line represents uh, the line x plus y is equal to 2. And we can now draw the parabola. The parabola x is equal to y squared, which is a parabola opening to the right vertex at 0, 0. Okay. Let us label this. This is the parabola x is equal to y squared. Okay, and we are referring to this region R. This is the region R, bounded by the parabola x is equal to y squared, and the line x plus y is equal to 2. Okay. Okay. Now, if we want to get the area by double integration, okay, the area, of course, is uh, the double integral of the differential of A. Now, if we want to show the differential of A, we have to use, okay, this element, okay. You can draw the element anywhere on the region. This is the element, which is a square, okay, and the sides are dx, and of course this is dy. And if we will get the area of this element, the area of this element is dx dy or dy dx. Hence, the area of the element is equal to the differential of A. And if we want to get the area of the whole region, we are going to evaluate the double integral over the region R. Okay, and please take note that the differential of A may be either dx dy, or the differential of A is equal to dy dx, depending on it is vertically simple or horizontally simple. Now, how do we know that it is vertically simple or horizontally simple? This is the same as, okay, saying whether we use the horizontal element or vertical element. Okay, now please take note that if we will draw any horizontal line, okay, in within the region, okay, it will always be bounded on the left by the parabola and on the right by the line. So anywhere we draw horizontal line, okay. So if we will consider a horizontal line anywhere on the region and it is consistent all throughout, then it is horizontally simple. So the differential of A is dx dy. And uh, actually, this is not vertically simple, okay, since if we will draw any vertical line within the region on the left side of the region, it is bounded by the parabola alone, but towards going right, it is bounded above by the line and below by the parabola. So it is not consistent. Hence, okay, we have the differential of A, or we will use the differential of A equals dx dy. Horizontally simple, similar to using a horizontal element. Okay, now the problem is how to get the limits of integration, and it will be based, of course, on the region R. Okay, so if we have the region R, and we will consider dx dy, okay, x will go from the left side, okay, the left end of the horizontal line, which is determined by the parabola, and going right to the line. So x will go from x left, and x left is y squared, to the line. Okay, the line is x plus y is equal to 2, and if we will express x in terms of y, then x is 2 minus y. Therefore, x will go from y squared to 2 minus y. Okay, and take note that y squared and 2 minus y are independent of x, and this will be used as the inner limits of integration. Okay, now what about y? Okay, y will go from the lowest value of y, which is -2, to the highest, which is 1. Okay, lowest is -2, highest is 1. Okay, hence y will go from -2 to +1. And we are going to use this as the basis for the limits of integration in the double integral of the differential of A over the region R. Okay, therefore, okay, going back here, then the area of the region R is equal to the double integral of the differential of A. Take note that we will consider the differential of A equals dx dy. So the inner variable of integration is x, and x will go from y squared to 2 minus y, and y will go from -2 to 1. And since the inner variable of integration is x, we have to evaluate the inner integral first, the integral of dx from x is equal to y squared to x is equal to 2 minus y. Hence, the area is equal to the integral from -2 to 1. Okay, the integral of the differential of x is x, and we have to evaluate this from x equals y squared to x equals 2 minus y, from left to right. Okay, then multiply this by the differential of y. Hence, the area is equal to the integral from -2 to 1. Okay, evaluating x at the upper limit gives us 2 minus y minus the value of x at the lower limit, which is y squared. So the integral becomes the integrand of the outer integral in y. So we have 2 minus y minus y squared. And evaluating the integral in y, integral of 2 dy is 2y, minus the integral of y dy is y squared over 2, minus the integral of y squared dy is y cubed over 3. Then evaluate this within the limits of integration from -2 to 1. So evaluating the integral at the upper limit, y is equal to 1, we have to replace y by 1. And that gives us 2 times 1 is 2, minus 1 square is 1, of course. So we have minus 1/2, minus 1/3, minus the value of the integral at the lower limit, y is equal to -2. So replacing y by -2, 2 times -2 is -4, minus -2 raised to the second power is 4, 4 over 2 is 2, and -2 raised to the third power is -8, minus minus is positive, so this gives us positive 8 over 3. Okay, close. And simplifying further gives us Okay, we have here -4, -2 is -6. So 2 minus minus 6 is 8. Okay, and then we have negative 1/2. And combining -1/3 minus 8 over 3, -1/3 minus 8 over 3 is -9 over 3, right? And -9 over 3 is 3. Now, 8 minus 3 is 5. 5 minus 1/2. And 5 minus 1/2 gives us 9 over 2. So the area of the region, okay, bounded by the parabola x equals y squared and x plus y is equal to 2, okay, is 9 over 2 square units. Now, we can actually interpret this also. 9 over 2 cubic units is the volume of the solid bounded by the region R, okay, and the height of the element or the height of the solid is 1. Okay, now, if we will recall what we had in module 2, finding the area bounded by curves, no? This is similar to finding the area using the horizontal element. Now, if we will use the horizontal element, the area of the horizontal element is the length of the element, which is x right minus x left. X right is 2 minus y, and x left is y squared. So that will give us 2 minus y squared times the thickness, which is equal to differential of y. And this will actually give us this one, okay? If we will use ordinary integrals, then the area is equal to x right, okay? We have x right minus x left. 2 minus y squared times the thickness dy. So that will give us, of course, the area is equal to 9 over 2 square units. Okay, so this is how to find the area by double integration. But of course, it is still more convenient to find the area by using ordinary integrals and using the rectangular element, which can be either horizontal or vertical. Okay, we just showed that we can also find the area of the region R by double integration. So let us have another example to illustrate finding the area by double integration. Okay, this time we will consider finding the area of the region R, where the region R is determined by the curves now, where x goes from -1 to 2, okay, and y goes from x squared to x plus 2. Okay, please take note that we are given the region R. Okay, we are not given the functions which are the boundaries of the region. Okay, but of course, if we are given y going from x squared to x plus 2, okay, we can consider y is equal to x squared, okay, reading from right to left, okay, y is equal to x squared, then y is equal to x plus 2. So we have y is equal to x plus 2. And if we want to draw the region, okay, we need to find the intersection of the two curves, y is equal to x squared and y is equal to x plus 2. So if we will do substitution, consider equation number 2, y is equal to x plus 2. Okay, elimination by substitution, we can replace y by x squared. So this is equal to x plus 2, and transposing x plus 2 to the left member gives us x squared minus x minus 2 is equal to 0. And let us factor the left member. Factors are x minus 2, x plus 1 equated to 0, and equating each linear factor to 0 will give us x is equal to 2 and x equals negative 1. Now, to find the corresponding value of y, we can just use equation number 1. And equation number 1 is y is equal to x squared. Hence, to determine the corresponding value of y, when x is 2, y is 2 squared or 4. Therefore, we have a point of intersection at 2, 4. And when x is negative 1, then the corresponding value of y is negative 1 squared, which is positive. Another point of intersection at negative 1, positive 1. So these 2 points, 2, 4, and negative 1, 1 are the points of intersection of the two curves. Y is equal to x squared and y is equal to x plus 2. Okay. Now, y is equal to x squared is a parabola opening upward with vertex at 0, 0. Okay, let us now draw the region R. Consider this as the y-axis, and consider this as the x-axis. So the points of intersection are at 2, 4. Okay, this is the point of intersection 2, 4. And the other point of intersection is at negative 1, positive 1, minus 1, 1. So if we are going to draw the line, just connect the two points of intersection. And this line is the representation of the equation y is equal to x plus 2. And the parabola y is equal to x squared with vertex at 0, 0 is this parabola. Okay, so this is the representation of y is equal to x squared. And we are considering this region R. Region R where y goes from x squared to x plus 2 and x goes from negative 1 to 2. Okay, now please take note that the leftmost value of x is negative 1 and the rightmost value of x is positive 2. So we have x going from negative 1 to 2 and y going from x squared to x plus 2. Hence, if we will draw the element, okay, this is the element, the differential of a, which is, okay, this is dx and this is dy. And it will be more convenient if we will consider drawing any vertical line. Take note that if we will draw any vertical line within the region, it will always be bounded below by y is equal to x squared and above by y is equal to x plus 2. So it is more convenient to use the differential of a is equal to dy dx. It is vertically simple. Okay, so go lower to upper. Y lower is x squared, y upper is x plus 2. So y goes from x squared to x plus 2, and x will go from -1 to +2. Okay, so from -1 to x is equal to 2. Okay, hence, if we will solve for the area, of course, the area of the element is the differential of a, and if we will evaluate the double integral over the region R, then the area is equal to the double integral of the differential of A. Take note that since it is vertically simple, then the differential of A is dy dx. And y will go from, okay, y will go from x squared to x plus 2. Okay, the given region. And x will go from -1 to +2. Okay, so evaluating the inner integral, the integral of the differential of y from the lower limit x squared to the upper limit x plus 2 will give us the integral from -1 to 2. Integral of the differential of y is y, to be evaluated from y is equal to x squared to x plus 2 times the differential of x. Hence, we have the integral from -1 to 2. When y is equal to the upper limit x plus 2, okay, that gives us x plus 2 minus, when y is equal to the lower limit, that gives us x squared dx. So we can now evaluate the integral in x, and the integral is equal to, okay, integral of x dx is x squared over 2 plus the integral of 2 dx is 2x minus the integral of x squared dx is x cubed over 3, and we have to evaluate this from the lower limit -1 to the upper limit 2. Okay, equals, when x is equal to the upper limit 2, so 2 raised to the second power is 4, 4 over 2 is 2. Okay, then plus 2 times 2 is 4 minus 2 raised to the third power is 8. So we have 8 over 3 minus the value of the integral when x is -1. Now, when x is -1, -1 square, of course, is 1. So we have 1/2. Okay, 2 times -1 is -2. And -1 raised to the third power is -1. Negative is positive. Okay, and if we will combine, okay, we have here 2 plus 4 is 6, minus 2 is 8. Okay, then we have -8 over 3 plus -1/3 will give us -9 over 3, which is -3, then minus 1/2. Okay, giving us 5 minus 1/2, and 5 minus 1/2 is 9 over 2. Therefore, the area of the given region, okay, is 9 over 2 square units. Okay, and if we will consider finding the volume of a solid whose height is equal to 1, and the region R in the xy plane is bounded by the two curves y is equal to x squared and y is equal to x plus 2, then this can also be interpreted as the volume of the solid, okay, whose height is equal to 1, so z is equal to 1, and the region is bounded by y going from x squared to x plus 2 and x going from -1 to 2. Okay, so this is just one application of double integrals. Now, finding the area by double integration. In our next session, we will have another application of double integrals, which is finding the volume by double integration, which is the real meat of the discussion.